Hey guys, hello everyone, welcome to the CSIR Academy, all of you. So, in this particular video, we are going to be discussing elimination reactions, and as you already know, that we are continuing a series of reaction mechanisms. So, I have started with the SN1 SN2 reaction, which is the basic reaction, the basic substitution reaction that we have already discussed. I hope that before watching this, you are also going to go and check out that video as well. Also, there are some really important concepts which involve the molecular orbital treatment of molecules, and try to discuss everything in detail so that the students who are preparing for IIT JAM exam or GATE exam or the CSIR NET examination or even for your MSc BSc level, the topic is going to be clear, very, very clear for all of you. Similarly, today I have taken elimination reactions and we are going to break it down once again because that way we'll be able to study it better. So today we are only going to discuss E2 elimination reaction, that also in detail, and we'll talk about all the important aspects of the E2 elimination reaction. Okay, and this series where we are discussing the reaction mechanism, I have tried to make these notes, these PDF PPTs from 4 different books, that is Bruce organic chemistry for Claydon, organic chemistry from Carruthers, as well as from Jerry March. So a compilation of all the 4 best books is here with all of you. You just have to go through the video and that's it for you all. You can directly make notes and the topic is complete for you all. All right. So yes, it's that easy. Let's start the discussion on elimination reaction. Okay. All right. First thing, that is, we generally, when we talk about elimination reaction, we have 2 types of mechanism. First one is the beta elimination reaction over here, as you can see, when there are 2 groups which are being lost from adjacent carbon atoms, that gives us a new double bond, which is termed as beta elimination reaction. Similarly, if there are 2 groups which are leaving from the same atom, that is from B over here, that gives you a carbene and sometimes a nitrene if it is a nitrogen. Alright, so these are the general 2 types of elimination reaction, beta elimination and alpha elimination, that we usually see. So, when we are talking about elimination reaction, we have also got to consider the criteria that for which type of molecule is going to undergo elimination, what will it give us, and which reaction is competing constantly with elimination. So, here you see, in addition to undergoing nucleophilic substitution reactions, alright, in addition to undergoing nucleophilic substitution reactions, alkyl halides also undergo elimination reaction. Now, in elimination reaction, atoms or group of atoms are removed from a reactant. As you can see that Y, which is supposed to be a nucleophile, sometimes it is supposed to attack over the CH2 to give you substitution reaction, but in certain cases it takes away a proton from this beta carbon and gives you a new double bond along with the elimination of H, Y and X minus. Now, when is this happening? How, what are the different factors that we have to take care of? We are discussing everything in this particular video. Now, most of the times we are confused about who is going to do substitution and who is going to do elimination. Let's look at a very, very simple compound. So you see over here, we are having a tertiary butyl chloride over here. And in the first case, if we take ethanol, so ethanol has a pKa. All right, here we are going to talk about pKa. So you must be clear about the pKa concept. This is going to give us a lot of idea about how the nucleophile affects elimination versus substitution, whether elimination is taking place or substitution, right? Very, very important. So when we are having ethanol, we say that it is a weak nucleophile. Alright. And when we are having ethoxide, it is a very strong nucleophile, and sometimes whenever it gets a possibility, whenever it gets a beta hydrogen, it's going to be working as a base. So what is the difference between a nucleophile and a base? That is the most important thing that you must know. So whenever any of the molecules, let's say this ethoxide, when any species has a greater affinity for a proton than for the carbon, okay, if any species attacks over this carbon, it is going to be termed as the nucleophile. And when any species attacks the hydrogen, it is going to be termed as the base. All right. Sometimes the same molecule, or let's say the same species, is going to behave both as a nucleophile and a base, given the structure of the molecule is different. Over here, the nucleophile is ethanol. All right. And the base is ethoxide. Yes, does it make any difference? It does, because the electron density on ethoxide oxygen is really high. It is having a full-fledged negative charge, and in ethanol, the nucleophile, it is working as a nucleophile because it only has a lone pair. All right, so that is the major difference. Greater electron density, and that also on the more electronegative atom like oxygen, that gives you a greater possibility of being a base, right, than being a nucleophile. And bases give you elimination, and nucleophiles give you substitution. Okay. Now here we are talking about the E2 reaction, as you can see. And in this particular reaction, in the E2 reaction, we see that the elimination, again, it is a beta elimination that we are considering, but it is elimination bimolecular. Now, what does bimolecular stand for? It is just simply that two molecules or two species are required in the rate determining step of the elimination reaction. All right. So you see that there is a OH minus which is going to remove a proton from either of these methyls. It is a tertiary butyl bromide. Any one of these methyl can provide a proton to give you an alkene in this way. All right. So as you can see, this is very similar to the SN2 reaction. It is bimolecular, requires two species, and also the rate is going to depend on both alkyl halide as well as the base. All right. So it is very, very similar to the SN2 reaction. Even the graph is same. All right. How do you plot the graph? From the reactant to the product, it is only going to give you just one transition state, no intermediates, right? So very, very similar to SN2 reaction. Now, trying to understand the E2 elimination mechanism in very, very simple terms. So there is a base, all right, let's say OH minus. It is going to remove a proton from the beta carbon. Which one is the beta carbon? The carbon which has the halide or a leaving group. That is termed as the alpha carbon, as you can see over here. This is the alpha carbon. And the carbon just next to it is the alpha carbon. All right, is the beta carbon, right? So this one is the beta carbon right over here, and from here the hydrogen is being removed. All right, so this is the beta elimination, E2 elimination. Now what is so specific about E2 elimination reaction? This is a one step reaction. All right, everything is happening in just one step. That is, the hydrogen and the leaving group are going to be in opposite to each other, and the base is going to approach the hydrogen opposite in the opposite direction to the Br minus which is leaving. Now this opposite direction has a huge importance for determination of the stereochemistry of the product. Okay, is it always the case? Do we have some exceptions? We are going to talk about everything in the upcoming slides. So 1,2 elimination or beta elimination reaction, one of the mechanism is one step elimination, that is E2 elimination reaction. So here you see E2 elimination have anti-periplanar transition states. So just now I told you that stereochemicality is very, very important to understand what is E2 elimination. Just now you have considered that there is a carbon which is going to have a, let's say, leaving group X. All right, and we want the hydrogen which is just opposite to the leaving group X. Why is that so? Let's see the reason. Now, new pi bond made up of old carbon hydrogen sigma and CX sigma star and sigma orbital. So what is happening? In an E2 elimination reaction, the new pi bond is formed by the overlap of the CH sigma bond and with the CH sigma star anti-bonding orbital. A sigma orbital and a sigma star anti-bonding orbital. So from the sigma and sigma star, how are we making the pi bond? Let's see. For making the pi bond, two of these orbital should be syn periplanar. What does it mean by syn periplanar? That is, they should be on the same side. They should be at least in the same phase. Okay? So what happens is, when we are having the carbon and the hydrogen, look over here, when we are having the hydrogen and the leaving group in the anti-periplanar form, which is a fully staggered form, then both of its orbital, this is the sigma star orbital and this is the sigma orbital, they are actually syn periplanar to each other. Alright, the orbitals are syn periplanar, and that is why it will be really good for their interaction in this way, and that is going to give you a new pi bond easily. Similarly, if we have the leaving group and the hydrogen fully eclipsed in this way, but what happens is these two orbitals are not going to, let's say we want to remove this hydrogen from here, this orbital and this orbital, they're actually making an angle to each other. As you can see, we don't want an angle, we want either 0 angle, 0 degree, or we want 180 degree. Getting the 0 degree angle is not possible. Okay, so that's why we get the 180 degree angle, and that is why we get the anti-periplanar rearrangement, which is the best for these two sigma orbital and sigma star antibonding orbital to make a pi bond. Alright. Now, how are they still forming the pi bonds? A lot of students might be confused. How are they still forming pi bonds from the sigma orbital and the sigma star orbital? See, the thing is, the carbon does not bring the p orbital or the pi orbital to make a pi bond, right? The orbitals transform into each other. So when I'm saying that the hydrogen is removed from the CH sigma bond, and from adjacent carbon the sigma antibonding is also empty, so it is available now. These two orbitals will take the form of a pi orbital and they will form the pi bond. They are going to change themselves into pi orbitals. That is how a pi bond is going to form. So guys, talking about stereochemical aspects, since we were talking about the anti-periplanarity, it is going to explain a lot of different observations for the E2 reaction. That is, E2 elimination is a stereospecific reaction. What is stereospecific? Right? Stereospecific means it is going to give you one. Let's say you started with one diastereomer, it is always going to give you only one single alkene product. Okay, that is stereospecific, only gives you one stereoisomer in 100% concentration. Okay, so if we are starting with this particular bromide compound, this is one diastereomer, this is another diastereomer. So we see that E2 elimination in the presence of a base like OH minus will always follow the same mechanism. That is, the hydrogen and the bromide should be anti-periplanar. So we are going to rearrange the molecule. Just imagine this molecule is rewritten in this way so that you can get the hydrogen and the bromide on the anti-periplanar position. Then remove the HBr and then see who are together. In this Newman projection, it is very, very simple to visualize. Okay, every time you're not supposed to write, but it is very easy to visualize over here. So this hydrogen and the bromine are anti-periplanar to each other, and if they are removed, you will get this pH and the methyl on the same side. Okay, as you can see. Okay, so this particular diastereomer will always give you E alkene, and in this way, in this diastereomer, when it is redrawn in this way, it is always going to give you the Z alkene, and that is stereospecificity. That is only one stereoisomer from this mechanism. All right, always anti-periplanar. That is the criteria that we have learned of. There are more stereochemical aspects that we are going to study, and also we are going to see regioselectivity, which is very, very important. So as you can see over here, we have these two terms known as stereoselective and stereospecific. All right. So stereoselective reaction gives one prominent product because the reaction pathway has a choice, right? It has a choice. It can go through either this intermediate or that intermediate, and hence it gives you two products. Okay. Either the pathway of lower activation energy is preferred, which is the kinetic control, or more stable product is preferred, that is the thermodynamic control. We have this option in the E1 reaction. So we can say E1 elimination is stereoselective, which goes through a carbocation formation, we will see eventually. But stereospecific reactions lead to the production of a single isomer as a direct result of mechanism of the reaction. Matlab ki the mechanism is as such that you're always going to have only one stereoisomer as the product. There is no other choice. The reaction gives a different diastereomer of the product from each stereoisomer of the starting material. So if you're taking one diastereomer, you get the same, you get one product. For different diastereomer, you get the other product, just previously we have seen. Okay. Now, stereo specificity, we will see eventually. I've taken some really good example from Jerry March and um, from Carruthers also, but now we will also see E2 reactions, regioselectivity, which is again very, very important. We will combine these two terms to explain the reaction of a lot of compounds. So here E2 reaction is regioselective. Now what is regioselective? You are getting an alkene, right? So alkene is not a functional group which can be you know, regioselectivity simply means putting the alkene on different carbons, or let's say at different position, just that. So here you are having a 2-bromopropane compound and you have the methoxyanion over here, but this is a symmetrical compound. So from wherever you are attacking the proton from, there are two beta carbons which are the same. So from wherever you take away the proton from, it's going to give you propene. But in this slide, if you see, you are having 2-bromobutane. Now this 2-bromobutane is unsymmetrical bromide. You are having two different possibilities of alkene formation. Now, if the methoxide or any other base is removing a beta hydrogen from here or from here, you are going to get two different alkene, 2-butene and 1-butene. Now, the question is, which is more stable? Definitely the more substituted 2-butene is more stable. That is the thermodynamic product. And which is less stable? 1-butene is less stable. That is the kinetic product. But the 2-butene forms as a major compound. Temperature is not mentioned. Nothing is mentioned over here. So how are we going to know that which alkene forms in a greater amount, which is going to be the major product? Now, there are some factors. There are like 4 to 5 factors which we are going to study to predict that which alkene is going to form in major amount. But first you have to know that we have terms for these alkene. The more substituted alkene, let's say this one, the 2-butene that we have formed, the more substituted alkene is sometimes it's known as Saytzeff alkene or Z-save alkene, right? And the less substituted alkene is the Hoffman alkene. Okay. So when are we forming the Saytzeff alkene or the Z-save alkene? We are going to see over here. Now this one, a very, very important, criteria, or let's say a very important factor. We will number it factor number 1, which determines which alkene you are getting. Okay. So bulky base gives major Hoffman alkene. Always remember, because we have data supporting this, right? Ye dekho, this is your compound, this is your alkyl bromide, for example. It is extremely unsymmetrical because you have how many beta carbons? You have one over here, another and another. You have 3 different beta carbons over here, right? So which beta carbon is going to be replaced by the RO minus? You see that these two are the same methyl, the terminal ones are the same methyl, and this is different. Alright, this CH is different. More stable alkene will be obtained when you are removing the CH proton. Less stable alkene will be obtained when you are removing any of the methyl protons. Fine. Now, look at the base choice. Number 1. If you are taking the ethoxide base, you get 79% of the more stable alkene, 21% of the less stable alkene. If you are taking a bulkier base, that is a tertiary butoxide base, then you get 27% of the more stable and 73. So the ratio has just inverted, the equilibrium just inverted. So when you are taking a bulky base, you will ensure that you are getting more and more of the less substituted or the Hoffman alkene. Similarly, third base, you see over here, it is even more bulky because the CH3 has been replaced by the ethyl. So even less percentage of the more substituted alkene and more percent of the Hoffman product. Similarly, bulkier the base, once again 92% of the Hoffman alkene you're getting. So first factor that we have seen is the bulk of the base. Bulkier the base, better is the yield of the Hoffman alkene. Okay. Now you see factor number 2 over here. So this is the factor number 2 that we see, all right. In the factor number 2, we see that alkyl chlorides, bromides, iodides, these preferentially form the more stable product, that is the Saytzeff product. Okay. So here we are taking an unsymmetrical alkyl bromide, the same ethoxide base over here, that removes a proton from the middle, this one more substituted carbon, and gives you 70% of the 2-methyl 2-butene, which is the Saytzeff product, and only 30% of the less substituted or the Hoffman product. And also in the case of chlorides, when you have two different possibilities of hydrogen, one here and here, the same base will give you major amount of the more substituted Saytzeff product and less amount of the mono substituted product. Okay. However, the the alkyl fluorides preferentially form the less stable alkene. Okay, because as you see over here, we are going to discuss why is that so. You see 2-fluoropentane, which is again an unsymmetrical fluoro compound, in the presence of ethoxide gives you 2-pentene, 30% only, and 1-pentene as a major product. That is the Hoffman product is major. Why does it happen? Let's see. So carbanion-like transition state is obtained when the methoxide is approaching this hydrogen and the CH2 is having a negative charge. All right, because the fluoride is a good will be a leaving group over here, so it has to leave. Okay. Now what happens is, in the case of fluoride, transition state leading to 1-pentene is more stable as compared to transition state leading to 2-pentene, which is actually going to have the delta negative charge on this central carbon over here. All right. So the carbanion like transition state in the case of fluorine is always more preferred to be on the less hindered or on the terminal side as compared to the more hindered side. Okay. So guys, in the presence of fluoride, when you are taking the fluoride F, as you have seen in the previous slide, all right, fluoride is more electronegative. It is smaller in size but more electronegative. And I think that the incoming base, which is going to grab a proton, which is opposite of the fluoride, the less hindered proton will be more acidic because the fluoride is having a hyperconjugation effect. I have shown you this hyperconjugation before also while we were discussing the important, the stable configuration of 1,2-difluoro ethane compound. Okay. So what happens is the hydrogen which is directly opposite, or let's say this is the fluorine, this is the carbon, and this is the hydrogen. For the fluorine, right, fluorine is going to leave. It already has a very high minus I effect on this hydrogen. Now, if the hydrogen is on the less hindered side, it is going to be more acidic, and if the hydrogen is on the more hindered side, the hyperconjugation effect is not going to be that evident. All right. In the case of chloride, bromide, iodide, it is not the hyperconjugation that is working. It is only the minus I effect. Okay. They don't show as much hyperconjugation as fluorine does because fluorine is very highly electronegative. Alright, so for chloride, bromide and iodide, it is only the case of minus I effect, but here it is hyperconjugation. Alright, so that is why it is really important that we understand why fluoride gives you let's say the less or the Hoffman product basically. All right. Now here we have another very, very important example, and these examples are from Carruthers. Okay. This is factor number 3, that how are we going to decide the Hoffman or Saytzeff product. Factor number 3 is effect of the bulky leaving group. So you have seen the bulk of the base determines the product. We have seen the alkyl halides will determine the product. We have seen the effect of bulky leaving group. So if you are having a simple alkyl bromide like this one, all right, it is unsymmetrically unsymmetrical compound halide, so it's going to give you elimination either from this hydrogen or from this hydrogen. 81%, as you see, bromide gives you majority of the Saytzeff product. So majority 81% gives you the Saytzeff and only 19% of the Hoffman product. But if we have a very bulky leaving group, what is this? It is a quaternary ammonium ion, and it wants to leave readily as soon as possible because nitrogen is having a positive charge. Okay, so when you are having this quaternary ammonium ion, whenever you see it, 100% you're going to get the Hoffman alkene. Look over here, only 2% or only a very little ratio you are getting the Saytzeff product. Maximum 98% you are getting the Hoffman alkene, which is the less substituted alkene. So this is our factor number 3. Okay. Now next is the factor number 4 that we see. It is the effect of bulky substrate. So bulky base, bulky leaving group, and now bulky substrate. Okay. So look over this compound. Compound number 1. Again, an example from Carruthers, William Carruthers. Cl minus is a good leaving group. Fine. Cl minus is, as I said, the chlorides and the bromides and the halides will give you a more stable product. Okay. But this example is an exception. Why is it? Why does it make an exception? Because you see that the chloride has again two possibility, one over here, another over here. Even if you are taking a not very bulky base, even if you are taking a ethoxide base, या फिर let's say not ethoxide, let's say a methoxide base, which is like even smaller than ethoxide, even that base is going to give you majority of this product. Why? Because the substrate itself is very, very bulky. So the base does not want to approach this more substituted carbon or the proton. It is going to readily take away a proton from here, from the outer methyls, and readily give you the Hoffman product. So when I say that the alkyl halide, chloride, bromide and iodide will give you the Saytzeff product, you also have to see that the substrate structure is not very, very bulky. If it is too bulky, it's going to give you majority of the Hoffman alkene as well. Now guys, this example that I have put up over here, it is to determine the stereoselectivity of the E2 reaction, and I would say stereospecificity of E2 reaction. This example is taken from Jerry March. All right. You see, elimination of HBr from meso 1,2-dibromo 1,2-diphenyl ethane. This particular compound, the meso form, gives you a cis isomer, and the DL pair will both give you the trans isomer. This will always happen. Always the meso compound will give you cis. Why is that so? Because a meso compound is having a sigma plane of symmetry, and we want the anti-elimination to happen. The type of elimination is anti. Please remember, we are following anti-elimination in the E2 mechanism. So on a syn compound, meso is thin only because see, both the bromides, if you write it properly, you see that both the bromides, all right, just write the bromide over here roughly. Both the bromides are on the same side, okay, and both the hydrogens are on the same side. All the groups on the there is a mirror image in between the molecule. So on a syn compound where the groups are on the same side, if we are doing anti-elimination, it will give you a different product. And on an anti compound where already the groups are trans, that is going to give you a different product. Okay, so what do you have to do over here? if you are doing HBr elimination, let's say we are doing HBr elimination, let's say hydrogen from here and the bromide from here. It is not simply going to be like this. You have to redraw the molecule in such a way that hydrogen and Br are opposite to each other, and then only you will be able to see cis or trans. So please do this by yourself. You have to be able to write the anti-periplanar conformation either in Newman or in Fisher, wherever you, in whatever way you want to write it in the anti form and then check, is it giving the cis? It will. Elimination of HBr. Similarly, elimination of HBr from the DL pair or from the active compound is going to give you the trans compound. As you can see over here, the H and the Br are already anti-periplanar over here. You don't have to draw anymore. So this pH and this pH, they are in the opposite direction, you see, because they are already anti-periplanar, right? So very, very important example, considering what is what stereochemistry will result into what product. Okay, so similarly here in this particular example, you see we want to eliminate a Br2 minus Br2 over here. How is it possible? How do we remove a Br2? Elimination of a bromine gas itself. So it has also been asked in your CSIR exam. You can take sodium iodide because one of the bromide, let's say there are two bromines anti-periplanar to each other like this. So one of the I minus is going to attack one of the bromides, which is basically going to be a delta positively charged bromide. And then the electron density falls over like this to the other bromide so that the Br minus also leaves. Okay. So from a meso compound, I have written the meso compound in the anti-periplanar form already. Now if you see you are attacking this bromide with the iodide, the bond falls up and this bromide eliminates, you get a trans compound. Alright, and for this dibromo compound, it is a DL pair. So if you are doing anti-elimination on this, you will get a cis compound. Okay, so there's a trick, there's a very small trick that when you are doing elimination, anti-elimination from a syn compound gives you a trans product. Because it is anti-elimination, we are doing it on a meso compound, gives you a trans product, and anti-elimination from an active compound or a DL pair will give you a cis product. Okay, very, very simple. Try to draw this by yourself to understand. Now, guys, this is the most important example for today's session. That is, again, this from Carruther's, and it has also been asked in a previous year question. That is, you are given two different compounds like this. All right, you have got two quaternary ammonium salts. All right, and what is the difference between these compounds? The only difference is that the position or the stereochemical position of the quaternary ammonium group is a little bit different. The syn and the anti compound like that. Okay. The syn isomer and the anti isomer. Alright, the question could also be asked in this way. Now, what happens is the question asks you that what is the major product formed in the case of syn isomer, what is the major product formed in the case of anti isomer, and which isomer reacts faster. So this is very, very important. Multiple times it is asked in the exam. Now you see, you have to put this amine group in the opposite side of a beta hydrogen. So this is the beta hydrogen. You just have to like rotate the molecule and draw the perfect conformation where it is present opposite to this beta hydrogen. Once you have written it down, you can do the comparison that in the syn isomer, if you are making this conformation, the other two groups are not having a very bulky interaction. That is the phenyl, there's a methyl over here, and towards the phenyl there is a hydrogen over here. So this process is not involving a lot of steric hindrance. However, in the second one, towards the pH, you're having one more pH. So this is going to be a bit slow because two bulky groups end up on the same side while getting the perfect anti-periplanarity conformation. Okay, so hence the second one, the anti-isomer is going to be slower then the syn isomer, and it is going to give you a cis compound. We don't call it cis, we call it Z-alkene, because there are two different groups present on the different carbon, and here we get an E-alkene in the syn isomer. All right, so syn isomer anti-periplanar situation, we get the E-alkene. Anti-isomer anti-periplanar situation, we get the Z-alkene. So yes, guys, this is it for today, and we have discussed a lot of organic chemistry, elimination reaction. I'm going to see you all in more such videos. Please go through all the important concept and make notes directly from the video itself, and also share it maximum with your friends so that the videos help a lot of people. Thank you so much. I will see you in another such video.